Hey guys, Math 6500, more on logistic regression. I will tell you I'm back in my office for this video and maybe the next 2 or 3, whatever. And so much more comfortable. It's kind of hard teaching the other videos when I couldn't see what I was writing. So if I misspelled anything, I'm actually a pretty good speller. I couldn't see. All right, guys, what I want to do in this video is address the assumptions for logistic regression. And as you would expect, they're slightly different than for simple linear regression or multiple regression. Because simple linear regression, we have that a linear relationship between the independent and dependent variables should exist for obvious reason. It's a linear model. And that the errors are normally distributed, and of course we want equal variances of the errors. Well, things again are different for the logistic regression. First thing, and I'm not going to write these down until I get to the end because we've touched on some of this stuff ad nauseum. But first of all, the outcome has to be binary. We still have to have independence. Independence is a threat to any probability distribution. And since our p-values are calculated using the underlying probability distribution, independence is critical. But the other three I'm going to get into and write down, and really that's just the purpose of this video, is to expand up on this. Now the first one, technically, I guess the third one is we need an absence of multicollinearity. And I'm going to go through how we check that, and you should know that there's an R function to check that. Again, multicollinearity just tells us that we have two predictors. Multicollinearity focuses on our predictors, okay? And it just tells us we have two or more predictors that are highly correlated and are, in a nutshell, telling us or providing the same information. The next is we need a linearity, not a linearity, but we need linearity of the independent variable and the log odds. So in other words, this assumption requires that the independent variables, and I should say that the continuous independent variables So again, this linearity of independent variable assumption with the log odds is specific to continuous predictors. So if we have gender or some categorical predictor, this doesn't apply. Are linearly related to the log of the odds. And it turns out this is very, very easy to test using R. I don't think it's intuitively clear, and it's not within the scope of this class to make it intuitively clear. I'm looking more about the process and you understanding how to check the assumption and what the results tell us. But this is something that you could really dive into mathematically and theoretically that leads to some pretty interesting findings. The third, again, I should say the fifth, is we need large sample. Now, what does large sample mean? Because this is really kind of quote unquote. The way I think about this is we need at least 10 cases per predictor. But as you study this more and more and more, I don't know why I have this where It'd be much better if I go full screen here. And that doesn't suit me either. Let's see if we can make that a little clearer. Okay, there we go. It looks better. But you know, as you investigate this a little further, you see that this is actually tied back into pi, or what I would call, in this case, I guess I would focus on the 1 minus pi. So an important safeguard would be if you, well, I'll tell you what, let me just give an example. Let's say that we have the number of predictors is equal to 6, and the expected probability of your least frequent outcome is 0.2. So let's say you have, you know, 1,000 cases, and you have 80% ones and 20% zeros. So this would be the least frequent outcome, would be the 20%. Then what we would need here, we can determine the number of cases we need by taking the 10, which comes from needing at least 10 cases per predictor, times the number of predictors divided by the proportion, or the expected probability, of the least frequent outcome. So guys, if my mental math is correctly here, we would need approximately 300 cases. So again, it kind of violates in a sense, because just a straightforward approach, we need 10 cases per predictor. So if we have 6 predictors, 10 cases would say, well, we would be comfortable with a sample size of 60. But actually this factor here plays a role, so we would actually need a larger sample size. Let me grab another sheet of paper. Now, how do we test these? Well, the sample size is going to be really easy to to calculate. It's early in the morning. I haven't had my second cup of coffee yet, so it's actually not that early. It's almost 10 o'clock, but I still haven't had my second cup of coffee because I've been driving so much. But anyway, over here in R, you'll see that I've inputted, it's called logistic6.csv, and I'm pretty sure this is the same data set that we used previously. So if I want to, let's just figure out our sample size. So we have a length. Let's just go x1, for example. So we have a sample size of 98, and you can see that I have 1, 2, 3, 4 predictors. Now, if I do a table of my y's, you can see that I have 31 and 67. So let me grab my calculator. So 31 out of 98 would be my least, or the expected probability of the least frequent outcome. So we got 31 divided by 98. I couldn't read my writing there. So 0.316, right? Yeah. So what I can say is take my 10 times the number of predictors, which is equal to 4, divided by 0.316. So I need a sample size of about 127. And guys, I don't have it. So what I may want to do is cut down the number of predictors to where the sample size assumption is satisfied. All right, so second thing, let's talk about multicollinearity. Multicollinearity, again, is where we have predictors that are highly correlated, highly related, so they're telling us the same stuff. The easiest way to test this, well, guys, I'm getting the cart before the horse. Let's actually go ahead and create a model. And even though our sample size restriction states that we really should use 3 predictors instead of 4, I'm going to violate that just because it's a demonstration. Alright, so I have my model, and I can see from the model that we have, I don't like that. Alright, so we can see that x1 is significant at the 0.05 level, and x4 is significant at the 0.01 level, right? So to check for multicollinearity, we install the library for the CLAR package, and we get a warning message that said it was built under a different version. So we'll go ahead and see if the versions are compatible. So guys, it's a simple VIF for the model. We look at our VIFs, we see that everything, well, the highest is 1.26. Typically, as long as these are under 3, there's no threat to multicollinearity. Some textbooks even raise the threshold as high as 10. I think I feel much more comfortable in the 3 to 5 range. Now, what would we do if we did? Let's just say, what if that had turned out to be 12.5 instead of 1.26, okay? Then what I would want to do is I would examine the relationship between x3 and x1, x3 and x2, and x3 and x4. And the first thing I would do is I would drive it back into my theoretical framework and look at least examine the motivation for the study. And if there were one of these 3 variables, and who knows, maybe we need to delete x3. So in terms of the theoretical framework, I would delete the variable that's highly correlated with x3 that wasn't as important or wasn't as much of a threat to the theoretical framework of my study. So that would be the approach that I would take. I would rerun the model with that variable eliminated, rerun the VIFs, and go from there. Now, the linearity assumption for logistic regression, again, what we're doing, we're testing to see that there is a linear relationship between any continuous predictor and the logit of the outcome variable. And the assumption is actually tested by getting a lot of dinging here. It's dinging here because apparently my daughter's texting in. So anyway, I got sidetracked with that. But anyway, the assumption is tested by examining the significance level of what I call an added interaction term between the predictor and its log transformation. So a lot to say there. So let's see how it actually works. Okay, so what I would want to do is, first of all, I'd want to look at my data, and I can see that the only continuous variable that I have that's a predictor is x1. So I only worry about x1. So I'm going to create a new variable, log x1, and I'm going to take the log x1 and the interaction of it with x1. So I create a new variable. Now I'm going to go back to the original model right here, and I am going to add that interaction term in this model. Now, when I hit return and I'll get the summary of the model, I have tunnel vision. I'm not really concerned about how this changes the significance level of the other 4 predictors. I have tunnel vision only on this predictor right here. Because if you'll notice, when I entered this, that x1, which was statistically significant before, is no longer statistically significant. x4 was significant before, and it still is significant. I don't care about that right now. The only thing I care about is that line or additional lines where I'm looking at the interaction between the continuous variable and the log of itself. Now, if the interaction term is significant, then the assumption is violated. Conversely, we can say, or in other words, we can say if the p-value is greater than 0.05, then the assumption of linearity of the logit has been met. So in our case, clearly we have a p-value greater than 0.05, so there would be no concern for the violating the third assumption. Now guys, again, don't report this. This is just to test the assumption. I mean, you would report it and say that it's the assumption, the linearity assumption for using logistic regression was tested by yada yada yada, and you would report this. You would report the z-value and the p-value, and but you wouldn't, after you reported it, you would go back to the original model in terms of making heads or tails about the relationship between the variables. Guys, I think that is all. Assumptions for logistic regression, because it uses maximum likelihood estimation, is a lot easier. Not as much as with simple linear regression or multiple regression. All right, guys, that's it.